And now in this lecture we find out the distance between the centers of two circles. In the drawing we have rectangle ABCD. We know that side AB of this rectangle is equal to 7 units in its length, side BC equals to 24 units. In addition, we know that inside this rectangle we have those two circles, and the center of this circle is here at point Q. The center of this circle is here at point P, and our mission is to find out the distance between the centers of those two circles, that is to say, the length of line segment QP. Okay? So, because of the fact that ABCD is a rectangle, you know that all the angles inside the rectangle are right angles, so those four angles, they're all right angles, so I'll write it down. So actually, this angle equals to 90 degrees. This angle also equals to 90 degrees. This angle equals to 90 degrees. And finally, this angle is also equals to 90 degrees in its sides. And because of the fact that ABCD is a rectangle, we know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side DC. But AB is 7, therefore DC must be also equal to 7 units in its length. Likewise, according to the sum rule, in rectangle ABCD, side BC equals to side AD. But BC is 24, therefore AD must be also equal to 24 units in its length. In the next step, we'll implement the Pythagoras theorem on the right triangle, triangle ABC. So on the right triangle, triangle ABC, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle, triangle ABC is AC, therefore the square of the hypotenuse is AC squared. And it must be equal to AB squared plus BC squared. Repeat again. In the right triangle, triangle ABC, according to the Pythagoras theorem, AC squared equals to AB squared plus BC squared. So AC squared, that is the square of the hypotenuse in the right triangle ABC, must be equal to AB squared. AB is 7, therefore AB squared is 7 squared, that is 49, plus BC squared. BC equals to 24 units in its length, therefore BC squared is 24 squared, that is 576. So it will find out that AC squared equals to 49 plus 576. So in total, AC squared equals to 576 plus 49 is 625. here we take a root out of this equation and we get that AC equals to the square root of 625, this is actually 25. So the length of the hypotenuse AC is equal to 25 units. And the hypotenuse AC of the right triangle ABC is equal to 25 units in its length. AC equals to 25 units. This circle is blocked by the right triangle ABC, while this circle is blocked by the right triangle CDA. So both those two circles, they are blocked by right triangles. In the next step, we'll develop a new formula that will help us to find out the radius of any circle that is blocked by a right triangle. So here we have the radius of this circle is equal to x according to our definition. This circle is blocked by the right triangle ABC. So in the next step we will develop a new formula that will help us to find out the radius of this circle that is x only by knowing the side lengths of this the right triangle ABC that is blocked, blocks this circle. Okay, so we define the point of tendency of tangent BC with this circle as point M. So actually PM is the radius of this circle. The radius PM is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, we get that this angle equals to 90 degrees. And this angle will be also equal to 90 degrees according to rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. AB is tangent to this circle here at point M. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule number 1. So we can actually implement rule number 1 in our drawing. Actually, we have already implemented rule number 1 here. According to rule number 1, tangent BC is perpendicular to the radius MO. We'll implement rule number 1 again. We define the point of tendency of tangent AB with this circle as point N. In the next step, we join points O and N together by a straight line. ON is the radius of this circle that is equal to x. So actually, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. So inside quadrilateral ONBM, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral ONBM, we have 4 right angles. Therefore, we can relate to this quadrilateral ONBM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, ON must be equal to the opposite side, MB. But ON is x, therefore MB must be also equal to x units in its length. Likewise, according to the same rule, in rectangle ONBM, side OM must be equal to side NB. But OM is x, therefore NB must be also equal to x units in its length. So actually we found out that quadrilateral ONBM is not a rectangle but a square. Why? Because of the fact that all of its sides are equal to each other. Each side of this square is equal to x. Okay. What is the length of this line segment AN? From the drawing it is very easy to see that AN equals to AB minus BN. That is to say, AN equals to AB, that is A, minus BN, that is X. So in total, AN equals to A minus X. I will remind to you that according to our definition, AB equals to A, BC equals to B units in its length, and the length of the hypotenuse AC is 3 units. So, what is the length of this line segment CM? From the drawing, it is very easy to see that CM equals to CB minus BM. Again, CM equals to CB minus BM. So CM equals to CB, that is B, minus BM, that is X. So in total, CM equals to B minus X. So we can write here that CM equals to B minus X. So here we have rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have here the common external point, point P. From the common external point, point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this rule number 2, PA equals to PB. So whenever you draw from a common external point to a circle two tangents, then the length of those two tangents must be equal to each other. In this case, PA equals to PB. So we can actually implement rule number 2 in our drawing. Why? Because in our drawing, we have the common external point, point A. We define the point of tendency of tangent AC with this circle as point S. From the common external point, point A, we have two tangents to this circle, tangent AN and tangent AS. And according to rule number 2, they are equal to each other. That is to say, AN equals to AS. But AN equals to A minus X, therefore AS must be also equal to A minus X. Likewise, we focus on the common external point, point C. From the common external point, point C, we have two tangents to this circle, tangent CM and tangent CS. And according to rule number 2, they are equal to each other. That is to say, CM equals to CS. But CM equals to B minus X, therefore CS must be also equal to B minus X. So we can write here that CS or SC is equal to B minus X. So the length of the hypotenuse AC from one side it equals to C. But from the other side, the hypotenuse AC equals to AS plus SC. Again, the hypotenuse AC equals to AS plus SC. So we can write here that the hypotenuse AC is equal to C units. It is equals to AS plus SC. So C equals to AS is A minus X. plus SC. SC is B minus X. So in total, C equals to A minus X plus B minus X. So C equals to A plus B minus X is minus 2X. So found out that in total, C equals to A plus B minus 2X. We add 2X to this equation, and we get that 2X plus C equals to A plus B. Here we subtract C from this equation, and we get that 2X equals to A plus B minus C. Here we divide this equation by 2, and finally we get that X equals to A plus B minus C over 2. So here we found out the general formula for the radius of any circle that is blocked by a right triangle. So the radius X of this circle is equal to A plus B minus C over 2. Okay, the radius of this circle X equals to A plus B minus C over 2. Now we'll implement the new formula in order to find out the radius of this circle that is blocked by the right triangle, triangle ABC. So first of all, we define the radius of this circle as R. According to the new formula, because of the fact that this circle with radius R is blocked by the right triangle, triangle ABC, the radius of this circle R must be equal to AB plus BC minus AC over 2. Repeat again. The radius of this circle that is R, according to the new formula, the radius R must be equal to AB plus BC minus AC over 2. So the radius R is equal to AB, that is 7, plus BC, that is 24, minus AC, that is 25 over 2. 7 plus 24 is 31, minus 25 over 2. 31 minus 25 is 6, and 6 over 2 is 3. So finally we found out that the radius of this circle, that is R, and this circle is blocked by the right triangle ABC, the radius R equals to 3 units. Likewise, we find out the radius of this circle that is blocked by the right triangle, triangle ADC. We define the radius of this circle as X So according to the new formula, the radius of this circle X that is blocked by the right triangle CDA, it must be equal to CD plus DA minus CA over 2. Repeat again, the radius of this circle is equal to X. This circle is blocked by the right triangle ADC, therefore the radius of this circle, according to the new formula, the radius of X must be equal to CD plus DA minus CA over 2. CD is 7 plus DA is 24 minus C8, that is 25 over 2. 7 plus 24 is 31, minus 25 over 2. 31 minus 25 is 6, and 6 over 2 is 3. So finally, we found out that the radius x of this circle equals to 3 units in its length. So r equals to 3 units in its length, and the radius x also equals to 3 units in its length. Okay, in the next step, we will implement the Pythagoras. We will implement rule number 1 in this circle. BC, tangent BC is tangent to this circle here, so we define the point of tendency as point M. PM is the radius of this circle that is equal to 3 units. The radius PM is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MP. If BC is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Likewise, we define the point of tendency of tangent AB with this circle Sn. In the next step, we will join points P and N together by a straight line. So actually, Pn is the radius of this circle that is equal to 3 units. The radius Pn, the radius Pn is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So actually found out that inside quadrangle NPBM we have 1, 2, 3 right angles, therefore this fourth angle must be also equal to 90 degrees. According to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. So quadrangle NPBM has 4 right angles, therefore we can relate to this quadrangle as a rectangle. And you also know that the opposite sides of a rectangle are equal to each other. That is to say, NP equals to BM. But NP is 3, therefore BM must be also equal to 3 units in its length. Likewise, according to the same rule, in the same rectangle NPBM, side PM must be equal to side NB. But PM is 3, therefore NB must be also equal to 3 units in its length. So we actually found out that quadrangle PNBM, this quadrangle is not a rectangle but a square. Why? Because of the fact that all of the sides of this square are equal to each other. Each side of this square is equal to 3 units. We repeat all the same process in this circle. We'll implement rule number 1 in this circle. We define the point of tendency of tangent DA with this circle as point G. So QG is the radius of this circle, that is equal to 3 units. The radius QG is drawn to point G, that is the point of tendency of tangent DA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius QG. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We define the point of tendency of tangent DC with this circle as point K. We join points Q and K together by a straight line. So QK is the radius of this circle that is equal to 3 units. The radius QK is drawn to point K, that is the point of tendency of tangent DC with this circle, and whenever the radius that is drawn to the point of tendency, then tangent CD will be perpendicular to the radius KQ. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So inside quadrangle QKDG we have 1, 2 first angles, therefore the fourth angle must be also equal to 90 degrees. So quadrangle QKDG has 4 angles, therefore cumulate to this quadrangle as a rectangle, but we know that the opposite sides of a rectangle are equal to each other. That is to say KQ equals to DG, but KQ is 3, therefore DG must be also equal to 3 units in its length. Likewise, according to the same rule, in rectangle QKDG, QG must be equal to KD, but QG is 3, therefore KD must be also equal to 3 units in its length. So actually we found out that this quadrangle QKDG is not a rectangle but a square. Why? Because of the fact that all of its sides of this square are equal to each other. Each side of this square is equal to 3 units. Therefore, we actually found out that those two squares are identical. Why? Because each side of those two squares is equal to 3 units in its length. In the next step, we will extend the radius GQ of this circle by a straight line until it touches side BC of this rectangle ABCD. We define the touching point of the extended radius GQ inside BC as point T. So by doing this construction, we actually created here the big quadrangle DQTC. Inside this quadrangle DGTC we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. And therefore this big quadrangle DQTC that has 4 right angles, we can relate to this quadrangle as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side GD must be equal to side TC, but GD is 3, therefore TC must be also equal to 3 units in its length. Likewise, according to the same rule, in the big rectangle QDCT, side DC must be equal to side QT. But DC is 7, therefore QT must be also equal to 7 units in its length. I write it down here that this side QT is equal to 7 units in its length. In the next step, we will extend the radius NP of this circle that is equal to 3 units by a straight line until it touches side DC of this rectangle ABCD. And we will define the touching point of the external radius NP inside DC of the rectangle is point Y. Again, by doing this construction, we created quadrilateral NYCB. Inside this quadrilateral NYCB, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside the big quadrilateral NBCY, we have 4 right angles. Therefore, we can relate to this big quadrilateral NBCY as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle ABCY, side NB must be equal to the opposite side, YC. But NB is 3, therefore YC must be also equal to 3 units in its length. Likewise, according to the same rule, in the same rectangle NYCB, side BC must be equal to side NY. But BC equals to 24 units in its length. Therefore, NY must be also equal to 24 units in its length. So NY equals to 24 units. This side NY equals to 24 units in its length. In the next step, we define the intersection point between side QT and side NY. This point is point Z. And we will focus on the small quadrilateral ZYTC. Inside this small quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle, this fourth angle must be also equal to 90 degrees. So, because of the fact that quadrilateral ZYTC has 4 right angles, we can relate to this quadrilateral as a rectangle. And we also know that the opposite sides of this small rectangle must be equal to each other. That is to say, YC equals to ZT, but YC is 3, therefore ZT must be also equal to 3 units in its length. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that side CT equals to side YZ. But CT is 3, therefore YZ must be also equal to 3 units in its length. So we actually found out that the small quadrilateral ZYTC is not a rectangle but a square. Why? Because of the fact that all the 4 sides of this square are equal to each other. Each side is equal to 3 units. So we have in this domain 3 identical squares. 1, 2, and 3. All the sides of these 3 identical squares, each side of this those 3 identical squares is equal to 3 units. Okay. So we actually extended the radius Q, the radius GQ by straight line. In this way we got line segment GT. When you extend a straight line by straight line, the result is a straight line. So GT is one straight line, then equal to 7 units. Here, GT equals to 7 units in its length. GT equals to 7 units in its length. Again, GT is one straight line that is equal to 7 units in its length. So, repeat again that GT equals to 7 units. Minus GQ, that is 3 units, minus ZT, that is also 3 units. Repeat again, that the GT, that is 7, minus GQ, that is 3, minus ZT, that is also 3, must be equal to the missing side QZ. Repeat again. The missing side QZ must be equal to GT, that is 7, minus GX, that is 3, minus ZT, that is also 3. So in total, QZ, the missing side QZ, equals to 7 minus 3, 7 is 7 minus 6, that is 1. So we found out that the missing side QZ here, it is equals to 1 unit in its length. Likewise, we extended the radius NP by a straight line, and in this way we got line segment NY. Okay? When you extend a straight line by a straight line, the result is a straight line. So NY is one straight line, and is equal to 24 units. Here, NY equals to 24 units. So NY, that is 24, minus ZY, that is 3, minus NP, that is also 3. It must be equal to the missing side PZ. Repeat again, NY minus ZY minus NP must be equal to the missing side PZ. Again, NY is 24, minus ZY, that is 3, minus NP, that is also 3, must be equal to the missing side PZ. So PZ in total is equals to 24 minus 3 is 24, minus 6, that is 18. If we want to find out that the missing side PZ equals to 18 units in its length. So I write it down here. The missing side here, PZ, is equals to 18 units in its length. Again, QT is one straight line that is equal to 7 units in its length. Here, QT equals to 7 units. We will focus on this side of the straight line QT at point Q. Here, on this side of QT at point Q, the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of the straight line QT, which angles we have at this side of the straight line GT at point Q? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle here, so which angles we have here? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to the rule that I mentioned. So the missing angle here must be equal to 90 degrees. So this angle equals to 90 degrees. In the next step, we will focus on this side of the straight line DC at point K. Okay, so this angle equals to 90 degrees according to rule number 1. So in the next step, we will focus on this side of the straight line DC at point Y. Which angles we have at this side of DC at point Y? we have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to the rule that I mentioned. So the missing angle here must be equal to 90 degrees. Okay. So actually found out that inside quadrilateral QKYZ we have 1, 2, 3 right angles. Therefore this fourth angle must be also equal to 90 degrees. In the next step, we will focus on the upper side of the straight line NY at point Z. On the upper side of NY at point Z, the sum of the angles must be equal to 180 degrees according to the rule that I mentioned. So which angles we have at the upper side of NY at point Z? We have this angle that is equal to 90 degrees plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees. According to the rule that I mentioned, therefore this missing angle must be equal to 90 degrees. And because of the fact that angle QZP is equal to 90 degrees, it means that triangle QPZ is a right triangle. So in the next step, we copy the green right triangle QPZ in a new page, and we implement on this green right triangle QPZ the Pythagoras theorem. Again, by PT is an abbreviation for Pythagoras theorem. So actually, this is the right triangle QPZ that I covered from the original drawing. QZ equals to 1 unit in its length, PZ equals to 18 units in its length, and this angle equals to 90 degrees, according to rule number 2 that I mentioned. So in this right triangle QPZ, by PT is an abbreviation for Pythagoras theorem, so in this right triangle QPZ, we get that QP square, that is the square of the hypotenuse, must be equal to QZ square plus PZ square. So QP square must be equal to QZ square. QZ is 1, therefore QZ square is 1 square, that is 1, plus PZ square. PZ is 18, therefore PZ square is 18 square, that is 324. So QP square in total equals to 324 plus 1 is 325. We take a root out of this equation and we'll get that QP equals to the square root of 325. But 325 is 25 times 13. We can take out 25, we can take 25 out of the root. The square root of 25 is 5, so, and inside the root we have to only leave 13. In total, we found out that the distance QP, the distance between the centers of those two circles, that is the length of the hypotenuse QP, it is equals to either 5 times square root of 13 units, or in terms of numbers, it is equals to 18.03 units. And that is the answer to the question. In the next step, I'll summarize the lecture. We'll start here in the drawing. We have rectangle ABCD, side AB of this rectangle equals to 7 units in its length, side BC equals to 24 units in its length. Inside this rectangle we have those two circles. The center of the circle is here at point Q, the center of the circle here is here at point P. Our mission is to find out the distance between the centers of those two circles. That is to say, the length of this line segment QP. So because of the fact that ABCD is a rectangle, we know that all the angles inside the rectangle are right angles, so those 4 angles, they are all right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side DC, but AB is 7, therefore DC must be equal to 7 units in itself. Likewise, according to the same rule, side BC must be equal to side AD, but BC is 24, therefore AD must be also equal to 24 units in itself. Then we focus on the right triangle ABC. According to the Pythagoras theorem, in this right triangle ABC, AC squared equals to AB squared plus BC squared. Repeat again, in the right triangle ABC, AC squared equals to AB squared plus BC squared. So AC squared equals to AB squared. AB is 7, therefore AB squared is 7 squared, that is 49, plus BC squared. BC is 24, therefore BC squared is 24 squared, that is 576. So in total, AC squared equals to 49 plus 576, that is 625. We took out of this equation and finally found out that AC equals to the square root of 625, that is actually 25. So here, the length of the hypotenuse AC of the right triangle ABC it is equal to 25 units. So we know that the right triangle ABC blocks this circle, while the right triangle ADC blocks this circle. So in the next step, we developed a new formula for the radius of any circle that is blocked by a right triangle. The right triangle ABC blocks this circle, the radius of this circle is x. So our mission is to find out a new formula for the radius of this circle that is x, in such a way that we will express the value of x only by the side lengths of this right triangle ABC. So we define the point of tendency of tangent BC with this circle as M. So here we have rule number 1. The radius OM is drawn to point M, that is the point of tendency of tangent BC with this circle, and whenever a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Then we define the point of tendency of tangent AB with this circle as N. The radius ON that is equal to x is drawn to point N, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So inside quadrilateral ONBM, we have 1, 2, 3 right angles, therefore the fourth angle must be also equals to 90 degrees. So inside quadrilateral ONBM, we have 4 right angles, therefore we can relate to this quadrilateral ONBM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other, that is to say, ON equals to MB, but ON is x, therefore MB must be also equal to x. Likewise, according to the same rule, side OM must be equal to side NB, but OM is x, therefore NB must be also equal to x. So actually found out that quadrilateral ONBM is not a rectangle but a square. Why? Because of the fact that all three sides of this square are equal to each other. Each side of this square is equal to x units in its length. Here, AN equals to AB minus NB. That is to say, AN equals to A minus X. Therefore, and we found out also that CM equals to CB minus MB. That is to say, CM equals in total to B minus X. Then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From the common external point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA equals to PB. You can implement rule number 2 in our drawing. Why? Because in our drawing, if you focus on the common external point A, from the common external point A, we have two tangents to the circle, tangent AN and tangent AS. And according to rule number 2, they are equal to each other. That is to say, AN equals to AS. But AN is A minus X, therefore AS must be also equal to A minus X. Then we focus on the common external point C. From the common external point C, we have two tangents to this circle, tangent CM and tangent CS, and according to rule number 2, they are equal to each other. That is to say, CM equals to CS. But CM is B minus X, therefore CS must be also equal to B minus X. from one side we know that AC equals to 3 units, but from the other side, the hypotenuse AC also equals to AS plus SC. So we can write down that the hypotenuse AC is equal to C, it is equal also to AS plus SC. So C equals to AS plus SC. C equals to AS, that is A minus X, plus SC, that is B minus X. So in total, C equals to A minus X plus B minus X. That is to say, C equals to A plus B minus X is minus 2X. So in total, C equals to A plus B minus 2X. We added 2X to this equation and found out that 2X plus C equals to A plus B. Then we subtracted C from this equation and found out that 2X equals to A plus B minus C. Then we divided this equation by 2 and finally found out that X equals to A plus B minus C over 2. So the radius X of this circle that is blocked by the right triangle ABC, it is equals to A plus B minus C over 2. Now we can implement the new formula in order to find out the radius of this circle that is blocked by the right triangle ABC. According to the new formula, we define the radius of this circle R. The radius R, according to the new formula, must be equal to AB plus BC minus AC over 2. Repeat again. The radius R of the circle that is blocked by the right triangle ABC must be equal to AB plus BC minus AC over 2. AB is 7, plus BC is 24, minus AC that is 25 over 2. 7 plus 24 is 31, and 31 minus 25 is 6, and 6 over 2 is 3. So we found out finally that the radius of this circle R equals to 3 units. Likewise, we found out according to the same formula the radius of this circle that is blocked by the right triangle CDA. We define the radius of this circle as X. So the radius X according to the new formula must be equal to CD plus DA minus CA over 2. And again, the radius X according to the new formula must be equal to CD plus DA minus CA over 2. CD is 7 plus DA, that is 24, minus CA, that is 25 over 2. 7 plus 24 is 31, and 31 minus 25 is 6, and 6 over 2 is 3. So we found out that the radius X of this circle it is also equals to 3 units in its length. Then we implemented the rule number 1 here. BC is tended to this circle at point M. The radius PM is drawn to point M. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle equals to 90 degrees. We define the point of tendency of tangent AB with this circle as N. The radius PN is drawn to point N, that is the point of tendency of tangent AB with this circle. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. So inside quadrilateral PN, BM, we have 1, 2, 3 angles. Therefore, this fourth angle must be also equal to 90 degrees. So inside quadrilateral PN, BM, we have 4 angles. Therefore, we can relate to this quadrilateral PN, BM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, PN equals to BM. But PN is 3, therefore BM must be also equal to 3. Likewise, according to the same rule, PM must be equal to NB. But PM is 3, therefore NB is also 3. So we found out that quadrilateral PNBM is not a rectangle but a square. Why? Because of the fact that all of its sides are equal to each other. If we repeat on the same process, we will find out that KQDG is also a square, and each side of this square is equal to 3 units. So we have here 2 identical squares. Then we extended the radius GQ by straight line until it touches side BC of the rectangle at point T. In this way, we created the big quadrilateral GDGTC. Inside this quadrilateral, we have 1, 2, 3 angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, we can relate to this quadrilateral DGTC that has 4 angles as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, DG equals to CT, but DG is 3, therefore CT must be also equal to 3 units. Likewise, according to the same rule, side DC must be equal to side GT. But DC is 7, therefore GT must be also equal to 7 units in its length. Okay, side GT equals to 7 units in its length. Then we extended the radius NP by side line until it touches side DC of the rectangle at point Y. This way created quadrilateral NBCY. Inside this quadrilateral we have 1, 2, 3 rectangles, therefore the fourth angle must be equal to 90 degrees. Also, therefore inside quadrilateral NBCY we have 4 right angles, therefore can relate to this quadrilateral NBCY as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say NB equals to YC, but NB is 3, therefore YC must be also equal to 3 units in its length. Likewise, according to the same rule, side BC must be equal to side NY, but BC is 24, therefore NY must be also equal to 24 units in its length. Then we can find the intersection point here as point Z. So inside the small quadrilateral YZTC, we have 1, 2, 3 rectangles, therefore this fourth angle must be also equal to 90 degrees. So inside quadrilateral ZYTC, we have 4 rectangles, therefore can relate to this quadrilateral as a rectangle. Therefore side CT equals to side YT. CT is 3, therefore YT must be also equal to 3 units in its length. Likewise, in the same rectangle, side YC must be equal to side ZT. But YC is 3, therefore ZT must be also equal to 3 units in its length. So we found out that the small quadrilateral ZYCT is a square. Each side of this square equals to 3 units. So here NY is one straight line that equals to 24 units in its length. So NY minus NP minus ZY equals to the missing side PZ. Repeat again. NY minus ZY minus NP equals to the missing side PZ. NY is 24. ZY is 3 minus NP that is also 3. So in total the missing side PZ equals to 24 minus 6, that is 18. So here PZ equals to 18 units in its length. Likewise, GT is one straight line that is equal to 7 units. So GT minus GQ minus ZT equals to the missing side GZ. Repeat again. The missing side QZ. So the missing side QZ equals to GT minus GX minus ZT. GT is 7 minus GX, that is 3, minus ZT, that is also 3. So in total, the missing side QZ equals to 7 minus 3 minus 3, that is 7 minus 6, that is 1. So we found out that the missing side QZ equals to 1 unit in its length, and we already found out that PZ equals to 18 units in its length. Then we focus on this side of the straight line GT at point Q. Here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at this side of the straight line GT at point Q? We have this angle that is equal to 90 degrees plus this missing angle. In total they must be equal to 180 degrees. Therefore this missing angle must be equal to 90 degrees. We have already found out that this angle equals to 90 degrees according to rule number 1. Then we focus on this side of the straight line DC at point Y. Here, the sum of this side of the straight line DC at point Y, the sum of the angles must be equal to 180 degrees. So which angles we have at this side of the straight line DC at point Y? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees. So inside quadrilateral QKYZ, we have 1, 2, 3 angles. Therefore, this fourth angle must be also equal to 90 degrees. Then we focus on the upper side of the straight line NY at point Z. Here, the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of NY at point Z? We have this angle that is equal to 90 degrees plus the missing angle. In total, must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees. Then I copied the right triangle QZP in a new page and we implemented the Pythagoras theorem on this right triangle QPZ. This is the right triangle QPZ that I copied from the original domain. QZ equals to 1, PZ equals to 18. So according to the Pythagoras theorem, QP square equals to QZ square plus PZ square. So QP square equals to QZ square. QZ is 1, therefore QZ square is 1 square, that is 1, plus PZ square. PZ is 18, therefore PZ square is 18 square, that is 324. So in total, QP square equals to 324 plus 1 is 325. We took out from this equation and found out that QP equals to the square root of 325. But 325 is 25 times 13. We can take 25 out of the root. The square root of 25 is 5. So in total, this expression equals to either 5 times square root of 13 units, or in terms of numbers, the distance between the centers of those two circles QP, it is equals to 18.03 units. Okay, thank you very much.